Hello everyone, and yeah, right here we're back with CodeForces competition, Division 2 competition. This time I won't be commenting much during the competition because I really want to solve as many tasks and this gets me a bit tired. I was just solving EdCoder beginner contest, so but at the end, we will discuss the problems and we will take a look at all of the solutions separately. So if there's not much talk, I will be drawing and talking a little bit, but yeah. So, but feel free to rewind something or step forward. Also check out the other videos on my channel. I have a lot of other videos, and as always, click that like and subscribe button. It keeps me motivating. I can't stress that enough because I don't make money out of this. So yeah. Okay. 12 seconds. I have the CPH Judge and VS Code up and running. I'm actually right now uploading the EdCoder video, so add the background. Yeah, so let me just do this. Okay. Come on. This is way faster. So Dalton is the teacher of N students. Initially, I students share PI. It's guaranteed the permutation. The student is happy if her number is different from the number of her chair. In order to make this, can repeatedly perform the following: choose the student's swap. What's the minimum number required? One can show it under. Yeah. So so we want to make a derangement. It's the minimum number of from a permutation to make a derangement. For each of this, which is yeah. So yeah. Okay. It's let's go B. Longest pretest pass. Given a positive integer n, find the maximum size of an interval LR such that for every I in the interval, n is a multiple of I. N is a multiple of I. But n goes up to well, well, if n is oh, n is a multiple of I, so n divides I. So we want to find such that n divides each of these subsequently. Subsequently. N divides this means that so up to the square root of n, it's only possible in the fourth test case. It's very, very small. And this is very small. So these are very small numbers. But how do we prove this? It's probably primality something. I think 500 maybe. 500 and 4 zeros. 5 million. No, I'll put 600. I don't think it can go that high, but let's just be sure. C1. The only difference between two versions of problem constraint number of operations. You are given positive. You can perform multiple operations in one operation and set. So choose one integer and add it to the other integer. Make the array non-decreasing in most 50 operations. You don't need to minimize the number of operations. Okay, what about the C2? C2 is C2 is wait. This is hard. The hard version is 31 operations. Make the array non-decreasing. Non-decreasing in 50 operations. But the length of the array is up to 20. So C1 is like you copy the first, you on the last element, you add on the last element you add the, so you have some array on the last element. You want to make it non-decreasing, right? And you want to find okay, so I have all of these, but they can be negative, right? Negative. So if they're negative, it's something that it's different. It's like, let's say that we have some negative numbers here. These negative numbers these negative numbers so it's up to minus 20. It's up to minus 20. This is plus 20, this is minus 20. In case we have minus 1 here as the most negative number, we need lock-in operation to come to minus 20 here, this number. How much is this? Minus 1, minus 2, minus 4, minus 8, minus 16 here, and then minus 16. So we have all of these numbers we can arrive at. There's something easy. So each number, so let's solve C1 first. Each number would be so the numbers that are not monotonically increasing, let's say that here there's some other small, there's some number. Can I start from here, and on this number I add the previous number? This becomes bigger. And then on this number I add the previous number. This becomes even bigger. If there's a negative here, I add the wait. So what about if I take the maximum number and I add it here as many times as I need? And then if this is minus 20, I add one more. And then I add, it could be all negative somehow, right? So I add the biggest positive number here, and I make it positive, and then I make it positive, and then on the next number, when I add it here, it will make it even more positive. But then if I have a negative number here, so minus 1, and I have something positive and I add a negative number, then this becomes smaller. So you kind of wanna, on this number, add twice maybe this number. If they're all negative, I don't know what you should do. If they're all negative, they're all negative. Let's assume that they're all negative. I want on this number to add the most negative number. about some priority queue? I have this number and I fix it. I say, okay, this is fixed. And the next number is small. I want to find what is the smallest number, smallest positive number, so that this guy will make it a little bit fatter. And I copy this guy. And I go and I find another smallest negative number, non-negative number. And I do this. What about there's no number? No, there will be always a number due to the fact that this guy will be always bigger. Okay, so let's assume like that. So all negative. If A at J so what if this is negative? What if A at J is negative? Most 50 operations. I think they're all negative. Maybe we'll get some idea. They start here, this is the tip, and this is this. And then they're all negative. Adding this number to here will make it more negative. Adding this number to here will make it more negative. Adding this number to the prefix of negation. So there's some negation here, right? Adding this number will make it even more negative. So if they're all negative or all positive, it's fine. So if they're all negative or all positive, we just add the prefixes from backwards here. So it's 4, 5. So 4 is like 4 plus 4. Yeah, so that's okay. That's okay. If all negative, if they're all positive, it's the other way around. But let's say that there is something negative and something positive. Then what do you do? You want to make it like this, right? Can I shift all of these negatives up? Can I, if there's positive, I can make this guy here the most positive number. So I can make it them, I can add here the most positive number in 5 steps, and then I can iterate over there's 20 steps and make them all like positive. And now it's going to be like this. Then iterate one more time. So that will work for C1. That will work for C1. So if they're all positive, if all positive, then this is if they're all positive. But then there's something negative. Then here there's a guy that is negative. And now we want to, so there's C2 is like, C2 is only 31 operations. So you can, you can I want to make this the most crucial element, and then offset each of these elements. Pointer difference. So this is the max element. We'll get this element, and while so the max element can be added immediately to all of these elements. So we push this operation. This is in logarithmic time. This looks fine. This looks fine. This looks fine. Okay, this passes pretest C, but I mean C1, but C2 is it's not that easy. So how to optimize this? One pass should be made, and then the other pass is like 11 operations at most. What about D? What's D? He has a deck of n cards from top to bottom. Each card can be either locked or unlocked. Initially, the topmost card is unlocked. The game proceeds each turn. Chooses an unlocked card. The value card is V. Unlock the first V locked cards from the top. If they're less than V, earn V victory points. So either we earn V victory points or unlock cards. So the unlock, when you unlock a card, when you have something, you either unlock some cards from the top of the deck, or you gain these points. If it's the last card, you have to unlock cards on top of the deck when getting these points. It's not quite simple. It's not quite simple. Okay, let's consider solving C2. We have to, because only 5 people solved C2, so it seems hard. So how do you... Okay, so let's say that all of these are somewhere here. Very close, right? So if they're very close, somewhere like this. If they're very close, the maximum element is here, right? So we just have to add until we have this sorted. If there's something like this, I'm going to add on this element some negative element, like the largest negative element we could add. What about greedily? Just like giving the largest negative element won't do us much. There are always 10. There are always, like, the worst case, there's 10 and 10 cards on the positive side, and then there's like 10 cards on the 10 things on the negative side, let's say. If it's 50-50 ratio. Then these 10 things which are positive, we can make them negative by taking a negative number there's 2 operations that we need to take into account. Here, one operation, make this negative number a bit more negative. What about if the positive number is like this? Take which one has the maximum absolute value. In each of these numbers, which one has the absolute negative value? Then which of these has the absolute negative value? So yeah, so the maximum absolute value we can take and make them all of the other things equal and then prefix them. But that's not quite right, right? I mean, make either all negative or all positive. What if most of them are negative, but there's like a lot of one positive number, a big positive number. Then this big positive number to be made into a negative number, you kind of wanna no, there has to be another way of pulling this off. Maybe try to make this positive. Let's say this is positive, right? If we want, what if they're all negative? Then you want to add say this. Let's say that. So if they're all negative, well, what we did is we added this guy, we added upon this guy. And this guy makes now a prefix. And it goes monotonically decreasing. Let's assume that there's a positive guy. Let's assume that there's all negative and then there's one positive. Of course, it's very common. Just let's say that there are a couple of like this positive guys. You do prefixing, right? You come to this guy, which is positive. And now what do you see? If I add this guy, the prefix will look like this. But I don't want to do that. I want to take something here. So this prefix is the sum of all of these prior. What about if I can take this prefix and I can add it twice here? This guy. But maybe I will need to add multiple times. How do you prove that this is amortized? There's like 6 of these. And then there's 10 to fill. And 20 to prefix. take the absolute maximum and add it in itself. And then they're almost 10 different. If they're equally spaced, then so there's like 10 positive and then negative numbers. What about making a prefix like this? And jumping here, and then these have to be prefixed with I think you move this either in the negative direction or in the positive direction. You only need to move 10 of these, right? Let's say the 20 is the prefix is fixed. Then how can we get rid of these 10 without doing much work? So if this guy is very high, we need to lower them at least his size, which takes a lot more effort. So the biggest number here, the biggest maximum number, if I lower the biggest maximum number, then if I lower that to, well, if I lower that to 0, I can't lower the other. So you create some kind of prefix on this, and then wait, when it comes to this guy, I need twice to lower it, because one time I will lower it, and the other time what it will do is will the other time will it's still not 31. Ten of these lowerings is done. maybe you brute force the amount of if there are more positive things than negative. There are more positive things than negative. I'm not quite sure how I solve. So, okay, so imagine 50% of them are like here and 50% of them are here. There is sometimes when you can cancel out things. So take the biggest element, the biggest absolute element, and this biggest absolute element, if I can make it fast enough to become if I can make it in one step to become bigger than the other thing here, the element in the bigger side, so on the side where there are more elements, become immediately bigger than this side. Then what I can do is 10 steps fill all of these, then 20 steps, actually 19 steps do this. So this here is 19 steps. Let's say that 10 steps are needed to fill the other side, so there's like 29 steps. We're left 2 steps to make the biggest element bigger. And in 2 steps, if it's -2, I can just go to -4. This is if it's -1. But if it's -1, then the other side is like very big. and this other side can do all of so here's the thing. If the absolute value there's smaller number of elements here. Say this is they're bigger negative than positive. Bigger number of negative elements. There's up to -4. -8 minus this is not positive. What about if we say that try to start at somewhere here, add all of these, and then I think all of them have to be negative or positive. 35 is the best I can come up with. Yeah, so if I have this is like the maximum altitude. Altitudes that are smaller than this can be easily made into negative, that are equal and smaller than this be easily made into negative. Now that there are almost 10 of these that are in this range. Okay, so 10 of these can be converted to here. What about if there's a bigger value, like a lot bigger value? But now you cannot just convert that guy over to here. So like you have already used 19 plus 10. Technically, I'm not earning. Like, I mean, you can convert this, but it will be positive number here. Let's say, and then after here, then steeply goes negative. And then this positive number here, it's not easy to. So you will get it down a little bit. But after that, it's not clear how would you get it down further. It's a very balancing act of things I don't quite understand. We want to maximize the number of victory points. Okay, we take one card and then this opens up some other cards. Or it doesn't. This is not a... This is a hard problem. These are hard, really hard problems. See what? So he got some wrong cancer. Okay, 31 operations. I mean, it's not. It's not clear. "31 operations. Why? Why so little?" If it's bigger than this, you will down it down, but it won't go to 0. Maybe you could skip these somehow. Maybe the idea is, well, no, you can't do that because this grows. Maybe the idea is to get this, so to start either from here or to here, and then get me here the most integer, and then doesn't guarantee nothing. Like, I mean, I don't know how to prove something like that. It's not easy. So let's imagine something like this. This is the end, right? Okay, we have something here. Okay, we need 6 steps and we do these 6 steps. Then there's one thing here again, but then you can't just pop up this like that. So you have to design it such that this goes down quite a lot. Then you add all of them. See that there's 9 of these up. And all these are like that. So 9 of these up. There are 3 of this we can do. So we do like 1, 2, 3. And here they are, plus 20. So some case like this where this is some case like this. And then, okay, so we have like 9 of these 20s, right? 9 of 20s and 11 of the other guys. Now, positive and negative. Now you do one of these very negative. Let's pick this guy, or it doesn't really matter, this guy. You do up to 20, so there's 5 operations. 5 operations up to 20. And now you begin, you have 19, you have plus 9 operations. And plus 19, so you kind of want this, you need minus 32. And then prefix. And then here this, just prefix. And this minus prefix minus prefix. Plus this prefix twice. And then so forth. So 9 of these plus 19 of these. This is the best, I think. 28 plus 533. Right, but we need to think a little bit clever and design it a little bit better. See how many operations does it take to one test case, and then 20 of these, and then minus 120 minus 1. Minus 120 minus 120. 1 minus 1 these are 10, and then 10 more. Twenty-nine. 29. This is 29, but if this would be to reverse it, in case like this, 20 minus 21. So there's like 5 of these here, and then there's like 5 of these here. That's 38. But you could argue that you could try reversing this, but let's argue one more way. I want to argue that maybe it's not practical to do this, but maybe it's practical to do something like this. Let's see. Still 29. What about just trying to do one can argue that, okay, so I copy A, and then let's assume that if repetition is 1, then I will flip element and then do the same thing here. But then I want to go from the back side here. So if it's 0, it's this. And then else it's this is very close. It's definitely not correct. Well, I mean, it's correct, probably, right? Minus 20, minus 20, minus 20. These are all minus 20s. And then you do the other way around, is that you push yeah, so that seems correct. So that seems correct. I'm not sure though. I mean, try it both ways, and if it works one way, passes this. No, I don't know. I'm not sure whether or not this is correct, but we'll see. Earn or unlock the. I mean, I don't know this. The unlock first we unlock the cards. Earn the victory points. You want to earn as much victory points. What is the maximum number of victory points you can earn? You can earn maximum number of victory points is the sum minus n minus 1. This is the maximum number. So let me just say this. So the maximum answer is the sum of a minus n minus 1, because this will be used for opening cards. Sum of a minus a of 0, because a of 0 has to open some cards, and then minus n minus 1, or a of 0. So like is the maximum answer is maximum of these two values. Yeah, so we can earn these points, then do not open cards, or don't do it. But we can also open some cards. And as soon as I open some cards, I need to put them somehow in some priority cut or something, I don't know what. But then either I use a small number, which opens up more cards, small number of cards at the end, or I gain this number and I don't open cards at the end. But I want to open them in such a way that I open all of them. So I want to make n a sum of some integer. So I want the absolute difference between n minus 1, technically, because the first card is not so yeah, so I'm in brackets here, n minus 1 minus whatever I open, minus whatever I used cards, minus the sum of used cards to be minimized. This is what I want. I want to minimize this. But also sometimes I don't want to open cards that, but not really true when you have cards which are all zero, like after some index I. So you don't want to do this. You don't want to open cards after some index I. So you want to be clever about it. You want to be quite clever, right? So I start from the back of the array, and let's consider starting from index n-1. We know that if I access index n-1, I gain the n-1 points. But that's if I access. Okay, what about n-2? N-2, if I access -2, I either want to access more. It depends on how I access. How I access n-2. The int is n-2, then the answer is either a n-2 or tp of n-1, because the answer n-2 is either this or this, but then it's not the end. It means that there's something more, and if there's something more, I can just add to the answer n-2, because I mean, I don't know, maybe it's actually not worth adding to the answer. So how I access n-2 is very important. So this, you unlock some cards, and then when you unlock these cards, you say how the problem is, how do you what card should you use to unlock other cards? And should you use that? Another idea is to try to see what is the only unlocking zeros is not fine. Other things are fine. So let's consider, let's okay, so let's consider what should we consider? Let's say we have a frequency map. Then we add all of these in the frequency map and we consider unlocking cards, but what, from the smallest or from the biggest? Can you binary sort somehow? Can I pick these cards such that the answer, can I pick a sum of cards such that the answer is the middle value and still works? So if you consider that that an unpicked card will open many cards above. But what do you want to do? You want to pick the, so okay, so you pick the last card, and then prior to the last card, if some big number, you pick it. You pick it until there has to be a number. So each, no, I mean, each number, so there's some very weird, very weird. I mean, this is a good problem as well. Like S will have like this expected number of seconds until S is empty. This is the number of seconds when there's at least one of these true elements inside the set. And this is some kind of like this is some kind of this looks like a add color problem. It's all in like you either make this polynomial or you don't make it, or you extinguish. So pick an element X, and then you have to do this, or this is this very interesting animating to animate it. Like the things move. The things move, and they move in a very interesting. First, let's say these are the elements of the set. By this I mean this goes into the x direction, and then like you pick a random element, then you move it to the right. All the other elements stay in place. You pick again a random element, you move to the right. But then when this element comes to here, this element can kinda disappear. So if I move all this element here, here, and here, it disappears, and then now it's just these two elements, and this will be done, but after some seconds they all will disappear. It can be proven. I mean, it will be just only one left, right? And then this will be picked and this will disappear as well. I mean, it won't... Will it disappear? Pick an element, remove X from S. is smaller than m, so yeah, so there's some boundary m here, and after they all hit m, it'll just disappear, and that's why m is up to 500. So it's up to 500 because it's you don't I don't even have an idea for this problem. There was something similar, I'm pretty sure. How do you pick the lock cards? How do you pick them? Which of them? What is the gain? Up to some integer. So here wait. So up to some integer. So there's this array. If I know the DP, like this is some DP array, and I know the gain if I access this integer, if I access more than this integer, if I access more than this integer. So if I access this integer somewhere, and I use this integer to access v more integers from the point that, so the problem is, okay, if this access ends at this integer and I use v more integers to access here, it's querying for the maximum DP in this range, which we could easily do, right? But there is a problem in case you access more elements like this. Now the problem is that this integer can be used from here onwards, but it's not good. So, I mean, let's end it. Let's say that the access ends in here. We have some integers that we can use. Let's say that there's a frequency map of integers we can use. and I end with the access here at this point. And then I can try to use any of these integers and see what's the maximum DP in here in this range. Okay, we have the maximum DP in this range. And then we say that, okay, but this depends on the previous thing. I don't want to depend it here. I need to calculate the DP without a dependence. So if I have something V here that I can access, so if I access this guy however I want, I can then use my things to access more like that. Which is maximum DP, or this guy. So it's like the maximum of A at I and DP, and like maximum of DP of I to, so I plus 1 to I plus 1 plus V. So this here kind of does it. So this is the maximum, but what if I access this element and I kind of have more going on here? So what if we formulate one recursive formula? I have an element, right? And then I access some element. The recursive formula is what is the last element that I have access to what is the last element that I have access to. There are some unused elements, right? Or you could use the, you could make the status used element as well. Wait, if I access more elements, the thing is that accessing another element is not bad if this element is not 0, because the trick here is that, so if I can access more elements, I will access, because this will gain me 1. But if I have a 0 here immediately after the 1, I don't necessarily want to access this 0, because maybe like the and also I may be able to access interesting. What about if I always get the smallest number, the smallest thing that is like normal? get the smallest thing. Now access the next thing. The next elements. Here's the thing. Each element has some index, right? Some index. Now the idea is that to access this element, okay, we'll take the first element and access all of these elements. And all of these will have the cost of 0, right? Because we can get to that element with the cost of 0. But these elements will have a cost of 1, 2, 3. And now now let's say that this element has a value of 0, 4, and 2. Their values are actually -1, 2, and -1. Okay, let's say that this is 3. Let's say this is 3. Because if I take here all of these, so I want to get to this element, right? But this is the cost of the element here. Now, not necessarily I have an element equal to this cost. Hence the cost can be negative. So even though if in the ideal world, if I have all of these costs, then I can choose this here. But actually this is not this cost. Actually this guy here has a bigger cost. This guy doesn't have a cost of 0. This guy has cost of this plus this plus this, which is 7, minus their index 3, which is 4. This guy has a cost of 4. I mean a gain of 4. And this guy has a gain of 2. So, okay, so we have some gains here. So some gains. We have some negative, positive, negative, whatever. And now we have these integers, and now we want to extend them to some point where the gain is a positive number and we can reach them. So some like maximum point, maximum gain. If we extend to this number, then we can pick some other as well, some other number, then this gain would be always positive unless there are a lot of zeros, in which it will shortly become negative, like linearly fall. There could be a negative gain, but then there could be again a positive gain. So it's not okay. So it could be negative and then could be positive again. So I want to pick the highest gain possible. want to find, is there an integer such that this is the highest gain? I mean, with our given integers, which one can be the highest gain? And then after picking this, we have to calculate again. But this time, so we have a segment tree which minimizes this. I mean, doesn't minimize, it's like minus, do minus this, and then there's like a maximum function over the segment tree, and then the gain is calculated with like a periodic like this. Yeah, something like that, I would guess. So this segment tree, we want to have a lazy segment tree, essentially, right? So sparse seg tree, lazy sparse. I mean, I don't quite need a sparse seg tree, but I have the memory. Oh wait, where's this where's this implementation that I use? It's already with data structures like the segment tree. This is already with infinity up to 10 to the 18. Essentially, that doesn't really matter. Okay, like this. This is fine to be this, but this has to be long. This has to be long. Okay, and then no, so there's some array B, and then low and high is like 0 and B dot So this here is b of I is going to be equal to b of I minus a. Yeah, we need a prefix here. Whatever we gain prefix of I is prefix of I plus prefix of I minus 1 a of I b is prefix of I minus I minus I, and then we would, okay, we know that I don't know how do you even prove this? How do you even prove this? Prefix I minus I, right? Prefix I minus. Then we have prefix I minus. You gain the most, but do you actually gain the most? It's like short term. I see a couple of problems with my solution, that's why I uncoded. Like, you could choose this element, let's say that this is a maximum, then choose like something like that, but maybe you want to choose a little bit more so that like you then can access here this element, and if you don't choose then you will have problems accessing them. It's not an easy trivial problem at all. the elements are ordered like that, but only zeros can negate this down, so it's not like, and this makes it you see here this 0, and this one is negative gain, but let's assume that this is here a lot, so then making it, assume that this is again 0, 0, then making this one won't make it after. So if I have a case like this, 2, 4, 5, 0, 1, 0, 0, 0, and then some like very big number, then so these are separate numbers. Then you would choose these two, but then you would need to choose like 5 of them. You would have to sacrifice to get this one, and sacrifice and then to get this. So this could be divided in blocks like this, but even if there were all zeros, you could like sacrifice this 4 just to get the 100 here. Because this 100 has a very, very big value. So no matter how you take a look at this, you want to like sum up somehow to get to that number. That's why I think you solve this problem from behind, from the back of the array, because then the states become either locked or unlocked, and I think it becomes better, but I'm not sure. Okay, I won't solve this problem for 3 minutes, but I will discuss a little bit about the previous couple of problems. So the first problem, the problem A, Dalton the teacher. So you had some permutation, you wanted to make that in derangement, which means that no index of the permutation is the same as the number inside of the permutation on that index. And if you could imagine, like, let's say that there's like some permutation, then there's some numbers that fit the permutation. So this is the original permutation, the indices. Some numbers do fit inside the permutations while others don't match. And the trick is that you can always swap any number, so you can swap these two that fit and make them not fit. But what if you have like 3 numbers that fit, that are like this? So in this case, you would swap these two, but for the third number, you won't have like for the number that you won't have. You need to swap it again, and it doesn't matter what you swap. You will swap with like any number of the permutation, and that's why the solution is the count of these of the numbers that match with the indices plus 1, because if it's like an odd number, then there will be like an even number. So this is like a ceiling version of like a seal here, and then divided by 2. That's like because you need to match them with pairs. So that's pretty much it. That's pretty much it for the formula of the first. The second problem was kind of tricky. It asked for the largest, for the maximum size interval from L to R, like of the positive integers, such that for every integer I in that interval, n is a multiple of I, so n divides I divides n. And n goes to 10 to the 18, and you would see that in order a lot of these numbers to be multiple of n, which are consecutive, so let's imagine that you have like 100 and then 101, 102, 103, 104. You kind of see that if you multiply all of these together, because they have to be multiple of n, and then you would need to divide them by the is it the lowest common? Yeah, no, the GCD of these, something like that. But the GCD of two consecutive numbers is always 1, which means you have to divide it by 1. And then you kind of reach n really quickly. And you reach n extraordinarily quickly. So you don't need to check more than like the first 600 or something. I'm not like really sure, but like there wouldn't be many of these to check. I don't know how to prove that, so I would have to look up the tutorial, but that's the main idea behind it. So that should be system testing right now. Problem C, I don't even know if problem C would be enough to go by, to be honest. But C2, so I discussed problem C and I won't go a lot into it, but the whole idea is to make each number either positive or negative into the array, and then to go over these numbers and sum them up and make a prefix. If they're negative, the prefix starts from the last number. If they're positive, the prefix starts with the first number. And when you prefix positive numbers, you make a monotonically increasing array. When you prefix negative numbers from the behind, you make again a monotonically increasing array. Non-decreasing array actually, because they can be zeros as well. So yeah, that's pretty much it for the problem. Other than that, you have to be careful about like how you do this, but I take the most, like I try to do positive and I try to do negative, and I see which one has less than 31, at most 31 operations. And as soon as I find one that is most 31, I just print the operations in return, because I know that the other guy won't be done. And I try to maximize the maximum number, and then try to do, like, if it's repetition 0, then I do this, repetition 1. But if repetition 1, that means that I try to make them all negative, and I actually just reverse the sign, and this is kind of enough to a little bit like to shorten the code, but you could just copy and paste stuff as well. I don't know about problem D because I didn't solve it, but let's take a look maybe at some common standings where we would go to like page 1. Yeah, problem D. Well, let's take a look at some solutions. So problem D. So yeah, bitsets, no. I mean bitsets would be something of a cheating thing, no? Apparently no. Apparently bitset is fine. So if they read the array and they make a prefix sum, what we did with the prefix sum, we actually say that like, okay, what's the gain if I get to this point? Then if the prefix sum is smaller than I, he breaks. If not, he adds it. He adds the thing to this. And then if it's this and the maximum. Okay, this is some mathematics that I need to quite check in on, but apparently he tries to find what is the maximum he can I don't quite understand. So if this is smaller than I, it means that the sum at that point got smaller than whatever, so you can't get to that point. But otherwise you add this to the bit set, then you see if the bit set I is on, this means that you can reach to that point. Is the sum, maximum sum of I minus whatever it is used. So we reach that point. Also we can reach more points. We can reach further. Okay, I see. I understand. I think I understand. But yeah. So it's not actually shifting any bit sets. It's just using it as a Boolean array of like, can I arrive at that point, and then seeing if I can arrive at that point, and I can certainly get this sum, but minus I, because this will be used to get there. And also I can go over n, but in this time n is the maximum sum that I can get minus i's, because I use them. And this is pretty clever solution, I would say. Yeah, this is pretty clever solution. The resetting here doesn't really matter, but that's pretty clever solution. So yeah, thank you guys so much for watching, and I see you in the next stream.